Hi, with this video I want to talk about the univariate and bivariate normal distributions, or Gaussian distributions. So let's start with the univariate case. So let's say I've got a random variable x, and x has a normal distribution, or Gaussian distribution is another way to say the same thing. It's going to have the PDF as given here. So I've got my PDF notation for x, and then the functional form is basically e to the minus x squared. In this formulation, k and c are just constants. So it's e to the minus x squared. That's the key part of the functional form. So let's think this over. So if I plot, if I vary x, and I start at x equals 0, e to the minus x squared is going to look like this. So this is e to the minus x squared. So when x equals 0, then we get e to the 0, or 1. And then when we move, when x gets bigger or smaller than 1, this number gets, x squared gets bigger with a negative in front of it, then e to that big number gets smaller. As x tends towards positive or negative infinity, we've got e to the minus infinity squared, which is 0. All right? So this thing's defined from minus infinity to infinity, although the probability gets very small as you move away from the centroid. Okay, so then, so I like to think about that just to think about this functional form and see where this kind of classic bell curve shaped functional form comes from. But then we can put in some better constants than just this c and this k. So let's take a look at the second version down below. So now I've got my random variable x, the value x can vary. I've still got this x, e to the minus x squared here, but I just threw in a bunch more constants. So first of all, I'm going to take x minus the mean value. So rather than centering this bell curve on 0, I'm going to center it on the mean value of x, mu x. So in this figure below, the center is mu x here. And as x gets kind of bigger or smaller than the mean, this numerator is going to get bigger when I square it, and then e to the minus big number, it's going to tend to get smaller. Okay. Then in the denominator here, I've got this sigma x. So that's going to control the rate of decay, right? So when I've got a big sigma x, that means that I'm going to have a fatter bell curve. Right? So this, then as the numerator gets big, if I'm dividing by a big number as well, the total number is going to stay small, and so this bell curve is going to decay more slowly. All right? So that lets me control things. Then out front, I've got this this square root of 2 pi. This is just going to fix me up so that my probability density function actually has area equal 1, which it's required to have. And then this kind of 1/2 out here, I guess the sigma x out front also has to help me normalize my area to be equal to 1, because if the curve is getting fatter with the sigma x, I also have to divide by that bigger number out front to keep the area from getting bigger just because the bell curve got bigger. So that it gets fatter, but it also gets shorter because I'm dividing by a big number out front. And then the 1/2 kind of controls things so that because let me back up. Because I've centered myself on this mu x, the mean value of this distribution is mu x. So I've kind of by definition put in a parameter here, which is the mean value of the distribution. With the 1/2 here, that controls, that also varies the fatness of the bell curve, but it makes it so that the standard deviation of this distribution is exactly sigma x. So basically, I've cleverly put the mean value and the standard deviation of the distribution in as parameters of the distribution. Then the 1/2 and the square root of 2 pi and things just normalize me out, so I have a valid distribution. Okay? So even though this formula, the second formula here, looks kind of like it's got a lot of Greek letters and terms in it, there's not a lot to it. It's just this e to the minus x squared functional form, centered at the mean value that I'm interested in, and then with the sigma x tapering to get me a distribution that gets fatter or thinner to have the standard deviation sigma x. All right? And then some normalizing constants. So that's all there is to that. Okay, so let's talk about the bivariate normal distribution now. So this is a distribution that's got two random variables, right? So I'm going to talk about the probability density function for x and y jointly. So I've got a joint PDF here, and it's going to have the following formula. So if my PDF for x and y has this formula, I say that x and y are bivariate normal. And so let's take a look at this one. So I've got some terms that look kind of familiar. I've got a 2 pi out front, though not in a square root anymore. Got the sigma x and the sigma y out front, just like I had the sigma x out front in the univariate case. Now I've got one of those for each of my variables. Then I've got this kind of 1 minus rho squared in a square root and a 1 minus rho squared here. Here I've shortened my notation just a little bit so it doesn't get out of control. But this is just the correlation coefficient between x and y. So I've got a term related to the correlation between x and y. And then I have this term z here, which again, I kind of condensed down my notation to get this all into one formula. So z takes this value down here at the bottom. And the first term here, this looks just like the term that we had in the previous slide, the x minus the mean value of x squared divided by sigma x squared. And then I've got the minus 1/2 up above. So now because it's for x and y, as you might expect, I've got a second term that looks very similar for y. And then I've got a term that looks like it's got some kind of covariance looking thing in here, the x minus its mean, y minus its mean. And then I've got a correlation coefficient between x and y. And then instead of a sigma x squared or a sigma y squared, I've got 1h for the x and the y in the denominator. Okay, so what's going on here is we've still got a very similar functional form, but now it's in 3D. So I've got kind of x and y varying. And I've got this mountain of probability associated with this joint probability density function. And let's see, so what happens is when x is equal to its mean and y is equal to its mean, then all these numerators in the z all go to 0, and I have kind of e to the minus 0, and I have the highest value on this three-dimensional mountain. Right? So the peak in this thing occurs when y is equal to the mean value of y, and when x is equal to the mean value of x. That's kind of the location of the peak of the mountain. Now, and then everything else is, there's just kind of normalizing constants in here. Now, if I think about varying x and y, right, this PDF is going to, this is telling me the height of this three-dimensional mountain, and you can see in terms of the x and the y values, it just depends on z, right? And so as z gets closer to 0, we get to the peak of the mountain. And then as z gets bigger, I've got an e to the minus z, and my probability density will fall off. So I go down the mountain as z gets bigger. And I can look at this z term here in the second line, and this is the equation of an ellipse, right? So what I can say is if I've got this kind of center point in the ellipse of mu x and mu y, I've got kind of x, y values that shape out ellipses here. And these are all values that are, that kind of plug into this ellipse. And if z is equal to some constant as I travel around the ellipse, then all those x, y values are going to have the same height in probability density space, right? So, so these are ellipses of constant z values. Okay. And as I vary x away from its mean, or I vary y away from its mean, I go down a bell curve type shape. And then this, this term in the middle of z, this kind of lets my ellipse be off axis. So it doesn't have, my principal axes in my ellipse don't have to be in the x and the y directions. If x and y are correlated, then my principal axis can go in some sort of diagonal away. Okay, so that's what the functional form looks like for the bivariate normal distribution. And I guess I should say somewhere on here that this distribution is defined for all values of x and y, just like x went from minus infinity to infinity before. We can say minus infinity is less than x and y is less than infinity. Right? So you can plug in any value of x and y, and this function is defined. So that's the bivariate version of a normal distribution. And it's got some super cool properties. So if x and y has a bivariate normal distribution, so the PDF described on the previous slide, then it turns out that x by itself has a marginally normal distribution, and x given y also has a normal distribution. So conditional on a value of y, x is still normally distributed. Right? So the marginal distribution of x is pretty easy because the mean value and the standard deviation of x are written right into the to the joint distribution, I just use those same mean value and standard deviation of x with the univariate normal distribution, and that's my distribution of x. If I want a condition on y, right, I say, well, what if I say given that y is equal to 2, now what's the distribution of x? Well, if x and y are correlated, that knowledge of y is going to change my knowledge of the distribution of x, but in a very convenient way. So here we just have these conditional means and standard deviations at the bottom of the slide. So we say the conditional mean of x, given that y equals some number small y, well, it's the mean value of x plus some modification term, right? And this thing is, so small y is the number that we're conditioning on. So we'll say, well, let's take small y minus the mean. So that's kind of how far y varied away from its mean. And then there's just a bunch of like constants to kind of convert units and things like that. And that's going to be a modifier on the mean value of x, right? And then the standard deviation of x, given some value of y, is the original standard deviation of x times this term that's related to how correlated x and y are, right? So that's the definition. Let's go one more slide and look at this a little bit more. So what I say is that if I've got x and y that have a joint or bivariate normal distribution, and that's kind of illustrated here in the bottom right. So these ellipses down here in x those are contours of the bivariate normal distribution. All right, so we talked about those contours of z. Now if I specify that y, the random variable y, takes some particular value, y, now I'm saying, okay, well I know that y takes this value. What's the distribution of x, right? So so we know that x has a normal distribution still. It's got this bell curve shape to its PDF. And then the mean value is this conditional mean that we specified. And then the standard deviation, which is the square root of that moment of inertia, that's got this value given by the equation here also. All right, so I just take the univariate PDF formula, so we know it's normally distributed, so we can still use that same PDF formula. But rather than substitute in our regular means and standard deviations, we're going to substitute in these conditional means and standard deviations that are given below. All right, so that's the new mean and standard deviation of this red conditional PDF that I drew in on my picture down below. So the distribution type is unchanged. It's normally distributed. It's just the means and the standard deviations that I have to update. Conditional should be conditional mean singular and standard deviation. And those things are easy to calculate from the formulas here down below. Okay, so let's take a look at these. And we can see a few things. So what I'm saying is if the mean value of y, let's say somewhere like here on the figure, kind of in the center of that ellipse. So here I've got a y value that's bigger than its mean value. Then the new conditional mean of x, getting a little messy here, but that's okay. So this is the mean of x given y equals y. It's going to be a little bigger than the original mean marginal mean of x. And it's bigger by an amount that depends on how correlated x and y are, and how much bigger y is than its mean value, and then the standard deviations of x and y to normalize things out. Okay. And then the conditional standard deviation of x given y is going to be a little smaller than the marginal standard deviation of x, or equal to. So if this correlation coefficient is non-zero, either positive or negative, when I square it, I'm going to get a number that's bigger than 0, but also less than or equal to 1, because that correlation coefficient can't get bigger than 1. So this number inside the square root is going to be less than 1. When I take the square root, it's still less than 1. And so I'm going to modify sigma x to make it somewhat smaller than it used to be. Right? But we can also note that if the correlation coefficient between x and y is 0, then in these conditional terms, things simplify out a bunch, right? So I got a 0 correlation coefficient means that this whole modifier term goes to 0, and I'm just left with the mean of x. And if this correlation coefficient is 0 in the standard deviation equation, I've got 1 minus 0, which is 1, square root is 1, so I'm also unmodified. So in that case, the mean value of x given y is just the mean value of x, and the standard deviation of x given y is just the original standard deviation of x. Okay? So if the means and the standard deviations are unmodified, then, and the distribution is still normal, that means that the conditioning on the y didn't change my answer for x. All right, and we'll explore that just a little bit more in the next slide. Okay, so again, a lot of Greek letters on this page, but the concept is actually quite nice, that I've got this conditional distribution, which is normally distributed. I just have to do some arithmetic here in the middle of the slide to figure out the parameters to substitute into that equation. So that's nice. So here's a little bit nicer picture of those, that picture that I drew on the previous slide. So if I have that bivariate normal distribution indicated by the contours in the bottom plane of this 3D figure, I could condition on here a couple different values of y, and the distribution will shift left and right a little bit because of the mean value being dependent on the value of y. So for conditioning on y1 or y2 could change the mean value of x. The standard deviation conditional on y was actually not a function of the y1 or y2 value. So the standard deviation is going to stay fixed. The moment of inertia is going to stay fixed for these. And these conditional distributions are going to be normally distributed, though. So they do have this nice bell curve shape. So I can find this conditional distribution. And then if I want to find, say, the probability of x exceeding some value, I could just integrate that conditional distribution from x up to infinity, find this shaded area, and that answer could change depending on the value of y that I'm conditioning on. But this is all calculatable in principle. All right, one final result for this bivariate normal distribution. So let's think about what happens if that correlation coefficient is 0. So I just showed you a little bit with the conditional distribution. Interestingly, if I had a conditional distribution of x given y and rho was equal to 0, then I just ended up with my marginal distribution of x. So that's a good hint of what's going to happen here. So let's take a look at this bivariate joint normal distribution. So I've just got the PDF for x and y that's got that bivariate normal formula that I introduced a few slides ago, and where z's got this kind of big long thing here. So let's take a look at this formula and what happens if that rho term is equal to 0. All right, so x and y are uncorrelated. So let's see. So I've got a rho term of 0 here. So that if that's 0, then the 1 minus 0 square root, that's all just going to kind of disappear. The 1 minus rho squared here, if that's a 0, that's going to disappear. My denominator will just be 1. I've got in my z, I've got this rho term here. If that's a 0, then the whole middle term here is all going to 0 out if one of those terms is equal to 0. So that's all going to simplify down. And so now it's simple enough that I could substitute in the z up for that top formula. So let's try to write this out and see what happens. So the joint PDF for x and y, I'm left with out front, I've got a 1 over 2 pi sigma x sigma y. Then e to the minus 1/2. And then I'm just going to substitute z straight in here. So I've got x minus the mean of x over, let's see. So we'll square that. And I'll divide by sigma x squared. And then the middle term's gone. I've got y minus the mean of y squared divided by sigma y squared. And I think that's all that's left. So the middle term of z disappeared. The terms with the rows were just 1s, so I could kind of drop those out. Okay, so here's what I'm left with. But now I've got some terms with x's in them and some terms with y's in them, so let's try to separate those things out. So I'm going to take First, let's do all the x stuff. So I'll keep the sigma x up front. Then I've got this 2 pi that's neither an x nor a y, so I'm just going to take half of it for the front and then half of it for later when I get my y's. So I'm just going to take a square root of 2 pi up front. And then, let's see, give myself enough room. The other stuff from the front, let's put it in back here. So I've got another 1 over square root of 2 pi sigma y. Okay. And then I've got the exponential term here. So if I've got an e to the power, e to the a plus b, I can take that as e to the a multiplied by e to the b. So I'm going to take the x terms and the y terms and pull them apart into their own exponentials. The 1/2 will come with both of those. So up front I'm going to have an e to the minus 1/2 x minus the mean of x squared divided by sigma x squared. So that's all my x stuff. And then in the back, I'll have an e to the minus 1/2 y minus mean of y squared divided by sigma y squared. And we'll close the square brackets. Okay, so I'm going to pull all the x stuff and all the y stuff apart into its own terms. But then interestingly, if I look at these square brackets, so inside this first square brackets, that is exactly the normal distribution PDF from the univariate case that was our first slide of this video. So I'm going to write that as just the marginal PDF for x, right? So we said that if x and y are bivariate normal, then x is marginally normal, and it's got this mean and standard deviation. So that's just the PDF for x. The second term, same thing, but for y. This is the univariate normal distribution for y. So I've got the product of these univariate normal distributions. Right? And then a definition of independence is that if the joint distribution for x and y, the joint PDF for x and y, is equal to the product of the marginal PDFs for x and the marginal PDF for y, then x and y are independent by definition. So what we can say is that if x, do capital, so if the random variables x and y are bivariate normal, and uncorrelated, then they are independent. Okay? So that's a great property. And that's not true in general, right? That's x and y have to be bivariate normal for this to hold, and uncorrelated. If x and y are just uncorrelated, it's not necessarily the case that they're independent. Right? There are plenty of ways that x and y can have a joint distribution that's uncorrelated but not independent. However, if they're additionally bivariate normal, then they are independent. So that's a nice property of the bivariate normal distribution, and one that we can take advantage of. Okay, so that's some basic results for bivariate normal distributions to give you a hint how they work. They're not quite as bad as they might look at first if they look a little intimidating. And they've got a couple nice characteristics here that we discussed with regard to the conditional distributions and this independence property. So hopefully that's useful for you.